So I want you to just imagine holding water right in your cupped hands.
Okay, yeah.
You interlock your fingers, you squeeze as tight as you physically can, and, well, it still leaks.
Right.
Like, the water just always finds a way out.
Yeah, it drips because, well, your fingers are basically an imperfect boundary.
Exactly.
Yeah.
And no matter the force you apply, there are always these tiny microscopic gaps. And every machine we rely on, from like a deep-sea submersible to a jet turbine, is currently fighting and usually kind of slowly losing this exact same battle.
It is a relentless battle, yeah.
Right. And so, welcome to the Deep Dives. Today we're looking at this massive, incredibly detailed source document titled Sealing and Leak Prevention. And our mission today is to really explore the hidden infrastructure of civilization.
Which is a bold claim, but it's true.
It really is,
Right.
because we're talking about the unglamorous, highly engineered thresholds that literally make modern technology possible. Okay, let's unpack this. We're decoding how the simple act of separating the inside from the outside is actually this relentless negotiation involving tribology, fluid dynamics, polymer chemistry, and even, surprisingly, global supply chain ethics.
It's a massive negotiation. I mean, we walk through industrial plants or we look at aircraft engines and we just assume those metal casings are these solid, impenetrable fortresses.
Right, like solid blocks of steel.
Exactly. But they aren't. They are assemblies of discrete parts desperately trying to hold back immense thermodynamic forces that just want to escape.
Because fluids just naturally want to get out.
Right. And if you look at, say, a highly machined, perfectly polished steel shaft under an electron microscope, it doesn't look smooth at all.
Really? Even polished steel?
Oh, yeah. It looks like a jagged mountain range. It's covered in these microscopic peaks and valleys, which engineers call asperities. So when two pieces of metal meet, they don't actually sit totally flush.
Oh, wow. So they're basically just balancing on each other.
Basically, yeah. They only touch at the highest peaks. The rest is just empty space. It's like this whole labyrinth of microscopic canyons.
And if you introduce a pressurized fluid to that environment, I mean, that fluid doesn't care how tight your bolts are. It will just exploit those canyons.
They absolutely will.
Which honestly brings us to a fundamental definition in the source text that just completely reframed how I look at mechanical design. It states that seals do not create motion and they don't generate power.
Right. They just make those actions possible without loss.
Yes. Like, a machine without seals is basically like a sentence without punctuation. Everything just runs into everything else and nothing works. An internal combustion engine doesn't work just because you ignite fuel.
Right, because if it wasn't sealed, the explosion would just blow out the sides.
Exactly. It works because the piston rings and the cylinder head gaskets trap that expanding gas. They force that kinetic energy into the piston rather than letting it blow out. The energy is captured because the boundary actually holds.
And that right there is the core philosophy of the boundary. Sealing is quite literally a battlefield of physics. It's this constant standoff between fluid pressure, material deformation, surface finish, and thermal expansion and friction.
It's a lot of forces all at once.
It is. And the pressure differential, what the engineers call delta P, is the main driving force. Fluids have to obey the second law of thermodynamics.
Meaning they naturally seek equilibrium.
Exactly. They want to move from a state of high pressure to low pressure. So the higher that delta P across a barrier, the harder the sealing material has to work to plug those microscopic canyons we talked about.
But wait, if the fluid is always trying to escape, aren't we just relying on the seal to fight this totally losing battle against friction and heat? I mean, especially when things get hot.
Well, yes and no. Heat definitely makes the physics infinitely more complicated. Because first off, heat causes the metal housings to expand.
Which literally changes the physical dimensions of the gaps you're trying to plug.
Right. But more critically, heat alters the fluid itself. It drastically lowers the kinematic viscosity of oils and lubricants.
So they get thinner.
Much thinner.
Yeah.
A heavy gear oil that is like super thick and sluggish at room temperature becomes basically as thin as water at operating temperature.
Oh, man. So that hot, thin oil will just easily slip right through a microscopic escape path that the cold oil couldn't even penetrate.
Exactly, which introduces one of the most brilliant engineering paradoxes we face,
Yeah.
particularly with dynamic seals.
Dynamic meaning things that are actually moving, right?
Right, dynamic seals are boundaries where the parts are in constant relative motion.
Yeah.
Think of a spinning pump shaft. penetrating a stationary pump housing.
Okay, so if you have a shaft spinning at, say, 3,600 RPM,
Right.
and you need to stop high-pressure fluid from shooting out along that shaft, your immediate instinct is just to clamp a piece of rubber down on it as tight as possible.
Which is what people used to do.
But the physics of friction dictate that if you apply enough clamping force to stop all the fluid, the friction generated by that 3,600 RPM shaft will instantly melt the rubber. Like, it will just disintegrate,
It
right?
will completely burn up.
But then, if you loosen the tension to reduce the friction and save the rubber material, the high-pressure fluid just blows right past it. So it seems like this totally unwinnable scenario.
It is unwinnable if you rely purely on solid-to-solid contact. The solution to that friction paradox, and the source goes into heavy detail on this in the mechanical seal section, is to actually use the escaping fluid as a structural component of the seal itself.
Wait, really? You use the leak to stop the leak?
Kind of, yeah. In a high-end mechanical seal, you have two incredibly flat, very hard faces. One spins with the shaft, and the other one stays stationary in the housing.
Okay.
They're pushed together by springs, but the fluid pressure from the pump actually forces a microscopic layer of liquid literally between those two faces.
It's essentially intentional hydroplaning.
Yes, exactly.
Yeah. Like when you drive a car way too fast on a wet highway and your tires lift off the asphalt. The water pressure builds up under the tread and physically separates the rubber from the road.
But that is a highly accurate comparison. These mechanical seals are engineered to hydroplane constantly. They utilize a fluid film that is only like a few microns thick.
That's wild.
It is. That microscopic film provides what we call elastohydrodynamic lubrication. It keeps the two hard faces from physically touching and burning each other up.
But because the gap is maintained at such an incredibly tight tolerance, the fluid can't freely gush out. It just sort of weeps across the faces as a vapor.
Exactly. So the concepts of zero leakage and zero friction are fundamentally at war. Engineering a dynamic seal is really about establishing a highly controlled, microscopic leak.
So if sealing is really about managing this engineered stalemate, we should probably look at the actual roster of components deployed on this battlefield. The source text gives us this anatomy of containment, right? It analyzes 7 primary architectures.
Right, the main cast of characters.
Yeah, so we have gaskets, O-rings, mechanical seals, packing, diaphragms, glands, and lip seals. But I want to push back on something here because people use these terms interchangeably all the time.
Oh, constantly.
Like, isn't an O-ring just a type of gasket? And isn't packing basically just an old school term for a seal?
No, and that's a huge misconception. They're completely distinct, and misapplying the terminology actually leads to catastrophic design failures all the time.
Okay, so break that down for us based on the text.
Let's start with the stationary boundaries.
Huh.
A gasket is a compressible material placed between two flat stationary surfaces, typically something like pipe flanges.
Like the flanges holding 2 big pipes together.
Right, and the physics there rely purely on the bolts. When you tighten the bolt, you stretch the metal of the bolt slightly, and that acts like a really stiff spring that crushes the gasket material right into the asperities of the flange faces.
The microscopic canyons.
Exactly. Whereas an O-ring operates on an entirely different principle. It's an elastomer, a rubbery material, with a circular cross-section, and it sits inside a precisely machined groove.
So you don't just crush it flat between 2 plates like a gasket.
No, you don't. You squeeze it slightly during installation just to get it in there, but the real sealing force comes from the fluid pressure itself.
Right, the source mentioned this. The fluid enters the groove, hits the O-ring, and physically pushes it into the far corner of the groove.
Yes, and the higher the pressure, the harder the O-ring deforms into those microscopic leak paths. It's what we call a pressure-energized boundary.
So the fluid is actually doing the clamping work for you.
Correct. Now, contrast both of those with compression packing, which is heavily used in massive industrial valves and like older pump designs.
That's the stuff you literally stuff into the machine, right?
Yeah, packing is typically a braided material, graphite, PTFE, sometimes even Kevlar. You stuff it into an annular space around a shaft, which is called a stuffing box, and then you mechanically crush it from the top using a metal piece called a gland.
So it bulges outward against the housing and inward against the shaft. But packing represents a much older kind of brute force approach to tribology, doesn't it?
It does. It's very old school.
Because the text mentions that packing actually must be allowed to leak visibly. Like if you tighten the gland until the leak stops completely, the friction will just score the stainless steel shaft and burn the packing to ash.
Right. You are actively relying on a steady drip of the process fluid to carry away all that immense frictional heat. It is a completely controlled bleed.
Which is wild to think about, that a machine is designed to actively leak just to survive.
Yeah, and that's precisely why the industry largely shifted to end-face mechanical seals for high-speed critical applications. To achieve that micron-level fluid film hydroplaning we discussed earlier, which virtually eliminates the visible leakage and dramatically reduces wear on the shaft.
And then you have diaphragms, which seem to sidestep the friction paradox entirely.
They do, yeah.
Because a diaphragm is just a flexible, impermeable membrane. There is no sliding contact, no lapped faces, no stuffing box at all. It simply flexes back and forth to transmit mechanical force or pump a fluid.
Right, it maintains a 100% solid boundary. You see this heavily in pharmaceutical or highly toxic chemical pumping, where even a microscopic vapor leak from a mechanical seal is totally unacceptable.
To kind of ground this for you listening, think about where you interact with these every day.
Yeah.
Like the gasket is the seal on your refrigerator door. The tiny O-ring is inside your garden hose quick connector.
Yeah, great examples.
And the lip seal is what's keeping the oil inside your car's engine.
Yeah.
And that diaphragm we just talked about, there's one in your toilet fill valve right now.
Exactly. They are everywhere. But the trade-off with a diaphragm, for instance, is cyclic fatigue. It doesn't wear out from sliding friction, sure, but bending a polymer millions of times eventually causes the molecular chains to stress and rupture.
Because you're just fatiguing the material over and over.
Right, which brings up a really critical point the text makes. Mastering the geometry of an O-ring or a lip seal is totally useless if you fail at the molecular chemistry.
Ah, yes.
Like an O-ring in a garden hose and an O-ring in an aerospace engine might look completely identical, but their chemistry is worlds apart. A perfect mechanical design made of the wrong elastomer is just a guaranteed failure.
And the material science section of this document is really where the complexity scales up, because we use the term rubber colloquially all the time, but in industrial sealing, we're dealing with this vast spectrum of highly engineered elastomers.
Yeah, rubber is way too broad a term for what's actually happening.
And it all comes down to chemical compatibility. I was totally fascinated by the explanation of molecular polarity, because the rule of thumb in chemistry is always like dissolves like, right?
Yes, and that rule absolutely dictates the survival of the seal. Let's look at EPDM, which is a highly common synthetic rubber. EPDM has a non-polar polymer structure.
Okay, so what does that mean in practice?
Well, it means it's incredibly resilient against polar fluids, things like water, steam, or automotive coolant.
Yeah.
It also possesses excellent resistance to atmospheric ozone and UV radiation from the sun.
Awesome. Sounds like a great material.
It is, for those specific things. But if you take that exact same EPDM seal and you install it in a system pumping non-polar hydrocarbon oils like, say, aviation fuel or just standard hydraulic fluid, it is a complete disaster.
Because of the, dissolves like rule?
Exactly. Because the fluid and the elastomer share a similar nonpolar chemical nature, the oil molecules just easily penetrate the polymer matrix. The EPDM seal will literally absorb the oil, swell to twice its size, turn into this spongy mush, and completely blow out of the groove.
Wow. So it just dissolves itself, basically.
Pretty much. But conversely, you have nitrile, or NBR. Nitrile is a polar elastomer, so it repels nonpolar oils and fuels beautifully. It is absolutely the workhorse of the hydraulic industry.
But there's a catch, right?
Always. If you expose nitrile to the ozone in outdoor air, the ozone physically attacks the double bonds in the polymer chain. The seal becomes super brittle, these microcracks form all over the surface, and it loses its ability to push back against the metal.
So it fails purely from just touching the atmospheric air.
Yes.
Just from sitting outside.
Here's where it gets really interesting to me, because I want to highlight silicone. There is this massive misconception about silicone in the general engineering public, and honestly, just for regular consumers too.
Oh, absolutely. Silicone has this sort of mythical reputation.
Right. Silicone is heavily marketed as this premium, indestructible, aerospace-grade material. We see it in high-temperature automotive applications, in bakeware, and we just assume it's the ultimate solution for everything. But the text is actually brutal about its limitations in dynamic sealing.
It really is. I mean, it is a phenomenal material for staggered extreme temperature environments. Like silicone's backbone is made of alternating silicon and oxygen atoms, which is called a siloxane chain.
That bond is so much stronger and more flexible at extreme temperatures than the standard carbon-carbon bonds in regular rubber. So it will remain elastic at like minus 100 degrees Fahrenheit, and it won't melt at 400 degrees.
Which sounds amazing.
It does.
Yeah.
But that exact same chemical structure gives it truly abysmal tensile strength and virtually zero abrasion resistance.
Wow, zero.
Practically zero. If you use a silicone O-ring in a dynamic application where it has to slide back and forth against a steel cylinder under high pressure, that friction will literally tear the siloxane polymer chains apart.
So it just destroys itself.
Yeah, it will shred into confetti in no time.
Yeah.
You are sacrificing all mechanical toughness just to get that thermal stability.
So when you actually need both chemical inertness and extreme thermal stability in a dynamic environment, what do you use? Because clearly silicone won't cut it.
Right. For that, you have to move to the fluoroelastomers, which are commonly known in the industry as FKM,
Huh.
or under the brand name Vaton. Yeah. These polymers are heavily fluorinated. The carbon-fluorine bond is one of the strongest in all of organic chemistry. It essentially acts as a shield for the polymer backbone, protecting it from chemical attack.
So FKM will survive those hot, aggressive fuel mixtures that would just instantly dissolve nitrile or EPDM.
Exactly. It's
Mhm.
incredibly robust. But that chemical immunity comes at a massive financial cost. FKM compounds are exponentially more expensive to produce.
Right. And the text notes that when temperatures and pressures exceed the limits of any polymer, even the expensive FKM ones, we have to move entirely away from elastomers and into hard materials.
Yeah, polymers have a hard ceiling on what they can handle.
So for the faces of mechanical seals, the industry relies on advanced ceramics, like silicon carbide and tungsten carbide. And the manufacturing intensity described here is just staggering.
Unbelievable precision.
Because these faces aren't just molded or put on a lathe. Since they rely on that micron-thin fluid film to hydroplane, they must be astonishingly flat.
Yes. The terminology the industry uses for this measurement is light bands. After the carbide is formed, it goes through this intense lapping process.
Lapping, what exactly does that entail?
So lapping involves rotating the seal face against a heavy cast iron plate that's covered in a microscopic abrasive slurry, typically something like diamond dust.
Yeah.
They grind the face until its flatness is measured using the actual wavelength of a helium-neon laser.
You're kidding. A laser.
Yeah. We're talking about surface variations of less than 11 millionths of an inch.
That is just... It's hard to even conceptualize how small that is.
It is, because if the face is off by even a tiny fraction of a degree, if it has a microscopic wave to it, that fluid film we talked about just completely breaks down.
Right, the hydroplaning stops.
Exactly.
Yeah.
And the highest points of the spinning carbide will violently crash into the stationary face.
Ah.
And because it's a brittle ceramic, it won't just smoothly wear down. You get what's called heat checking.
Heat check.
Yeah, microfractures propagate from the thermal shock, and the entire face just shatters. It really highlights how sealing is an industry where failure occurs entirely on the microscopic margin.
And that margin applies to the elastomers too, doesn't it?
Right.
The text details how a tiny manufacturing defect on a $2 ring can destroy an entire hydraulic system.
Oh, easily.
Like when an O-ring is molded, the two halves of the steel mold have to come together. If they don't align perfectly, or if the injection pressure is even slightly too high, a microscopic sliver of excess rubber seeps out at the parting line.
Right. The industry calls that flash.
Flash. And to the naked eye, a little ridge of flash seems totally irrelevant, like you'd just ignore it. But when that O-ring is installed and energized by 3,000 psi of hydraulic pressure, that flash creates this uneven stress concentration against the metal groove.
Exactly. It prevents uniform compression, and that creates a microscopic channel.
And then the hydraulic fluid just forces its way into that channel, causing the rubber to extrude and kind of nibble away at itself until the seal fails entirely.
Yes. And the exact same principle applies to the machining of the metal shafts themselves. If you are installing an elastomeric lip seal on a rotating shaft, the surface finish of that steel, we call its raw value, must be exact.
What happens if it's not? Say if it's too smooth.
Well, if a machinist polishes the shaft too aggressively, say they leave a microscopic helical scratch from the polishing paper, that tiny groove acts almost like an invisible thread on a screw.
Oh, I see where this is going.
Yeah, as the shaft spins, that tiny scratch will actually catch the lubricating oil and physically pump it out from underneath the lip seal. It acts as a literal micropump, forcing a leak from the inside out.
Which creates a terrifying reality for technicians and engineers. I mean, if a seal fails because of molecular polarity or a microscopic lapping wave or an invisible helical scratch on a steel shaft, none of those things are visible to the naked eye.
No, they are completely invisible.
When a mechanic reaches into a bin for a replacement part, a highly engineered FKM O-ring designed for a jet engine looks and feels identical to a cheap nitrile O-ring designed for a garden tractor. They are both just black, squishy rings.
They look exactly the same, which forces the entire industry to rely on this highly rigid, codified language of identification. The supply chain simply cannot operate on visual inspection.
It's too risky.
Way too is. The text gives a deep dive into how standard seals are classified. Like you might see a label on a sterile bag that reads AS568214 FKM 75A.
Right. And to the untrained eye, that is just alphanumeric soup.
Totally. But to a reliability engineer, it is a precise set of operational parameters.
Let's decode that, because this is where the theoretical physics actually translates into real-world application. AS568 is the aerospace size standard for O-rings, right?
Right.
It guarantees the exact dimensional tolerances.
Ex-
And then 214 is the specific dash number, which dictates the exact inner diameter and the cross-sectional thickness. Then FKM dictates the chemical recipe. We know it's a fluoroelastomer, meaning it will survive high temperatures and aggressive hydrocarbons.
Spot on. And finally, the 75A is the shore, a durometer reading.
And the durometer measures the hardness, correct?
Yes, it measures the physical hardness of the rubber. A 70 or 75 shore A is a standard industrial hardness. But if you have an application with incredibly high pressure, a soft 75A elastomer might physically deform and just extrude right into the tiny clearance gap between the metal parts, completely shredding itself.
So you need something harder.
Right, you would need a harder 98 durometer compound to resist that extrusion. The code on the bag is quite literally the only thing standing between a successful repair and a catastrophic blowout.
The document uses a phrase to describe visual substitution that really stuck with me. It says, "A boundary can lie politely before it breaks."
That's a great line.
It really is. If you ignore the supply chain codification, if a technician grabs a nitrile seal instead of an FKM seal simply because it visually fits the groove, it will actually seal perfectly at room temperature during the hydrostatic test. It will completely pass inspection.
Oh, absolutely. It'll look like a perfect repair.
But then, 3 days later, when the system hits its 300-degree operating temperature, the nitrile will undergo rapid thermal degradation. It'll harden into plastic, crack, and suddenly release a high-pressure spray of flammable fluid onto a hot engine casing.
And that is exactly why this precise reliance on specific chemistry and geometry dictates what the text calls the economic triangle of the sealing industry.
The tension between the cost of the component, the cost of downtime, and the severity of the failure risk.
Yes, industrial buyers are constantly battling this geometry. I mean, why pay $400 for a proprietary specialized mechanical seal when a generic component from a catalog costs $40?
Because the part cost is completely irrelevant compared to the downtime cost.
Exactly.
If a generic seal fails in a primary cooling pump at a chemical refinery, the entire production line must be safely shut down, flushed, and locked out for repair. You are losing hundreds of thousands of dollars an hour in lost production, all to save, what, $360 on a piece of rotating silicon carbide?
It makes no sense when you look at the big picture. In high-stakes manufacturing, a premium seal is not viewed as a consumable part. It is treated as a highly leveraged insurance policy against catastrophic downtime.
Which exposes a massive vulnerability in global supply chains, honestly. Standard commodity seals like basic NBR O-rings or flat paper gaskets, they're manufactured by thousands of facilities globally. They're so easy to source.
Yeah, you can get them anywhere.
But what happens when you need a highly specialized, FDA-compliant diaphragm for an intensive care medical ventilator? Or a chemically inert perfluoroelastomer seal for a semiconductor manufacturing tool?
That's where things get terrifying, because those specialized, highly regulated compounds might only be molded by 2 or 3 specialized facilities on the entire planet.
2 or 3 facilities globally.
Yeah. So if global shipping lanes freeze, or a raw material shortage hits the chemical suppliers, you suddenly have multi-million-dollar industrial or medical assets sitting idle, completely paralyzed, for want of a 3-gram piece of vulcanized rubber.
And that desperation fuels a dangerous dark market, doesn't it? Counterfeiting.
Oh, it is a massive problem. Because like we said, you cannot verify the chemical integrity of a polymer just by looking at it. Counterfeiting seals is highly lucrative and incredibly difficult to police.
Because a fake O-ring looks just as good as a real one.
Exactly. A rogue supplier can take a cheap, low-temperature nitrile compound, mold it to the precise AS568 dimensions, package it in forged OEM bags labeled as aerospace-grade FKM, and sell it at a massive markup.
And the supply chain procures it, the technician installs it believing it meets specification.
And the failure occurs entirely unpredictably out in the field. It's incredibly dangerous.
Which transitions us directly into the legal and ethical battleground detailed in Section 5 of the document. Because this reliance on highly specific proprietary boundaries has made sealing technology a central flashpoint in the right to repair movement.
It is a massive point of friction right now between OEMs, original equipment manufacturers, and independent repair networks. And look, patents serve a legitimate purpose.
Right.
If an engineering firm spends $10 million developing a novel split mechanical seal geometry that perfectly balances hydraulic pressure to reduce face wear by 50%, they have a legal and ethical right to protect that intellectual property.
Sure, absolutely. But the text highlights how OEMs often manipulate this. They aren't always protecting a novel leap in fluid dynamics. Often they deliberately design equipment using proprietary, uniquely shaped elastomeric gaskets shapes that offer no thermodynamic advantage over a standard circular O-ring, purely to lock the end user into a closed repair ecosystem.
The agricultural sector is the prime example cited in the text. The massive right to repair settlements, such as the John Deere case, often revolve around exactly this issue.
Right, let's look at that. A farmer has a massive piece of agricultural machinery leaking hydraulic fluid. The leak is caused by a proprietary $5 rubber seal, but the manufacturer refuses to sell that seal individually.
Yes, they force the farmer to purchase the entire $800 pre-assembled hydraulic pump module.
So you are forced to throw away hundreds of dollars of perfectly machined steel simply because the manufacturer controls the supply of the rubber boundary. It artificially inflates repair costs, creates staggering amounts of physical waste, and fundamentally compromises the concept of ownership.
It does.
I mean, if you legally own a machine, but you cannot replace its degrading boundaries without paying a monopolistic toll to the manufacturer, your ownership is conditional.
It's a huge debate, and regulatory bodies like the FTC and the European Union are actively targeting this practice now. However, we do have to look at the fair case for OEM control, because the text points out both sides here. For specific applications, closed repair ecosystems are not about profit. They are about liability, traceability, and safety.
Okay, right. I am a staunch advocate for right to repair when it comes to my tractor or my dishwasher. But I have to play devil's advocate here too. If we are discussing the elastomeric diaphragms inside an ICU medical ventilator or the hydraulic lip seals actuating the landing gear on a commercial airliner, I absolutely want the OEM strictly controlling that supply chain.
Oh, 100%.
I do not want a hospital maintenance technician substituting a generic third-party diaphragm just to save $20.
And the regulatory frameworks agree with you on that. In those critical environments, the OEM must guarantee that the elastomer has been biologically tested for outgassing, or that the polymer chain won't suffer a glass transition failure at high altitudes.
Because lives are literally on the line.
Exactly. FAA traceability and FDA medical compliance require a locked supply chain. The ethical tension is determining where the line is drawn. A braiding system absolutely requires OEM oversight. A windshield washer pump really does not.
This whole issue of replacing seals and generating waste brings us to a really fascinating environmental paradox that the text explores. The sealing industry is, at its core, an environmental problem.
It is.
Because the vast majority of these compounds are petroleum-derived thermoset polymers. They require highly toxic precursors, extreme heat, and massive energy consumption just to manufacture.
And, crucially, they are virtually unrecyclable due to the vulcanization process.
Why is that? Why can't we just melt them down?
Well, when you create an elastomer, you take long, loose chains of polymers and introduce a curing agent, usually sulfur or peroxide, under intense heat and pressure. This creates chemical crosslinks between the chains.
Okay.
It's what gives the rubber its memory, its ability to deform under pressure and snap back into shape.
But those crosslinks are permanent.
Yes. You cannot melt down a vulcanized O-ring and mold a new one the way you can with a thermoplastic water bottle. Once it is cured, it is set forever. So every time a refinery replaces 10,000 gaskets during a maintenance turnaround, all of that cross-linked polymer is fundamentally a waste product. It goes straight to a landfill or an incinerator.
It is a massive environmental burden, yet the text introduces this concept of quiet conservation.
Yeah.
You have to measure the environmental cost of the thermoset polymer against the environmental catastrophe that polymer prevents.
It's a trade-off.
Right. What is the carbon footprint of manufacturing a handful of FKM seals compared to the ecological devastation of a million-gallon crude oil spill?
Exactly. The sealing industry prevents staggering amounts of fugitive emissions every single day. We are talking about preventing volatile organic compounds from evaporating at refineries, stopping highly potent methane from leaking out of natural gas infrastructure, and containing toxic refrigerants that actively destroy the ozone layer.
So the document concludes that in the context of leak prevention, the most sustainable seal is rarely the one made of biodegradable or green materials.
No, almost never. If a bio-based polymer lacks the chemical resistance to survive in a pipeline, and it degrades and releases 1,000 gallons of diesel fuel into a watershed, well, it was an environmental disaster.
So the most sustainable boundary is simply the one that possesses extreme chemical durability, maintains its pressure energization the longest, and prevents the larger systemic failure.
Yes, quiet containment is the ultimate form of conservation.
It is incredible to realize the weight these microscopic thresholds carry, and to fully grasp the sophistication of a modern hydroplaning mechanical seal or a fluorinated polymer. We have to look back at the history of how humanity wrestled with this exact problem.
Yeah, the text frames the history of sealing as basically the history of industrialization itself.
Because long before polymer chemistry, the fundamental physics of the boundary were exactly the same. The ancient Romans constructing aqueducts or Mesopotamian engineers building irrigation locks, they all faced the same problem. Joining two hard materials inevitably leaves a gap.
Right, and they just used what was available by bitumen, clay, animal tallow, oakum, and leather to create a conformable barrier. They were stuffing soft materials into hard gaps to hold back delta P.
The principles didn't change at all, but the severity of the forces skyrocketed during the Industrial Revolution. We moved from gravity-fed water to high-pressure steam.
Which was a massive leap. Steam engines required dynamic sealing. You had these massive steel pistons reciprocating inside cylinders at high speeds under immense pressure and heat.
And this is where compression packing truly evolved, right? Engineers were soaking braided flax in animal fat and mechanically crushing it around the piston rods.
Yeah, it was terribly inefficient. It leaked steam constantly, and it required daily tightening. But it fundamentally enabled the mechanized world.
But the modern era of precision boundaries really crystallized with two major leaps. The first was the end-face mechanical seal, patented by George J. Cook in 1905.
Right, Cook realized that trying to squeeze packing around a spinning shaft was ultimately a losing battle against friction. By moving the sealing interface to two flat faces perpendicular to the shaft, he enabled the high-speed centrifugal pumps that currently drive modern chemical processing and municipal water systems.
And the second leap was the standardization of the elastomer. In the 1930s, Niels Christensen, a Danish-American inventor, patented the standard O-ring sealing system.
It's such a brilliantly simple geometry.
A round torus of rubber sitting in a square groove. But it completely revolutionized aerospace and hydraulic engineering. It was incredibly compact, lightweight, and because it was pressure energized, it sealed tighter as the forces increased.
It is absolutely the bedrock of modern hydraulic design. But, the text doesn't just celebrate these historical triumphs. It explicitly uses history to illustrate the catastrophic consequences of ignoring the physics of the boundary.
Yes. The most profound and tragic example in the document is the Space Shuttle Challenger disaster in 1986.
It is a harrowing case study in material science. The Rogers Commission investigation pinpointed the failure entirely on the elastomeric O-rings in the field joints of the solid rocket boosters.
The design relied on those O-rings maintaining their elasticity to track the microscopic movements of the metal joint as it expanded under the immense pressure of ignition.
But physics does not negotiate with launch schedules. The critical failure was thermal. Elastomers have a property known as the glass transition temperature, or TG.
Right. And what happens at that temperature?
When a polymer drops below its tree, the molecular chains literally stop moving. The rubber loses its elasticity entirely and turns into a hard, brittle plastic.
Oh, God.
On the abnormally freezing morning of the Challenger launch, the temperature of the O-rings dropped well below their operational design limit.
So when the rockets ignited, the metal joint expanded, creating a gap. But because the rubber had reached its glass transition phase, it lacked the resiliency to push back and fill that widening gap.
It couldn't track the metal. The boundary was compromised, and the pressurized, thousands of degrees combustion gases bypassed the seal, acting like a literal blowtorch on the external fuel tank.
It is a devastating reminder that a seal is not just a piece of hardware. It is a highly sensitive chemical mechanism that absolutely demands perfect environmental conditions to survive.
Which brings us to the fascinating philosophical conclusion of the text. Because after walking through all this rigorous physics, the tribology, and the historical tragedies, the author abstracts the concept of the seal into a psychological framework, introducing this persona of Tira.
Yes, Tira. The text uses Tira as a symbolic representation of the ideal boundary. Tira embodies quiet discernment, wisdom, and patience. The central thesis is that a seal is a threshold component.
Right, it does not exist to erase the division between inside and outside. It exists to honor and maintain that division while allowing the system to actually function.
It is a brilliant analogy for systems theory. A mechanical seal allows the shaft to spin. It permits the necessary kinetic energy and mechanical interaction required for the machine to do its work, while strictly forbidding the vital fluid from escaping. It is a selective barrier.
It really is.
I kept thinking about this in terms of human psychology and interpersonal dynamics. We talk about setting boundaries all the time.
Yeah, that's a huge topic today.
And a toxic or unhealthy boundary is basically like a solid steel plate welded over a pipe. It completely isolates you, preventing any interaction, connection, or empathy. That's essentially a prison.
Exactly.
Conversely, having no boundaries is like an open, unsealed flange. You let everything in and you just bleed out your own energy and emotional bandwidth until you are completely depleted.
And that's where the Tira persona represents the elastohydrodynamic film we discussed earlier.
Oh, that's a great connection.
A healthy human boundary, much like a perfectly engineered dynamic seal, is a deliberate, highly calibrated threshold. It allows the necessary friction of human interaction. It permits connection, empathy, and shared work, while selectively preventing contamination, abuse, or the loss of one's core stability.
The wisdom of Tira is the discernment to know exactly how much pressure to push back with, balancing zero leakage of one's vital energy with the flexibility to remain dynamic.
It's a really profound realization. The molecular chemistry and fluid dynamics required to keep a water pump functioning perfectly mirror the psychological resilience required to maintain a healthy human mind.
If we synthesize everything we've unpacked today, we have journeyed from the microscopic asperities of machine steel through the relentless forces of thermodynamics and the friction paradox, deep into the molecular polarity of engineered elastomers.
You really have covered a lot of ground.
We've navigated the high-stakes economics of supply chains, the ethics of the right to repair, and the environmental reality that true conservation often relies on unrecyclable polymers. The ultimate takeaway from this source text is that reliability is never an accident, and it is rarely dramatic. Reliability is quietly, painstakingly maintained.
Yes. When a boundary operates flawlessly, whether it is deep inside a jet turbine or functioning within a human relationship, the reward is absolute silence.
The reward is silence. I want to thank you for bringing your expertise to this deep dive today. Navigating the complexities of these microscopic thresholds has completely changed how I view the mechanical world around us.
Oh, it was my pleasure.
And to you listening, I want to leave you with a final provocative thought to mull over as you go about your week. The source material notes that successful, highly functioning boundaries completely disappear from our awareness. We are so used to them working that we mistake their quiet, reliable function for mere absence.
We take them for granted.
We do. It makes you wonder, look closely at your own life. Look at your relationships, your workplace, your local community, or your family dynamics. What are the invisible seals in your world? What are the quiet, unglamorous routines, the unspoken compromises, or even the incredibly patient people who are currently absorbing immense pressure just to hold your systems together? And more importantly, what happens the day those invisible boundaries finally wear out simply because no one ever thought to recognize or maintain them?